Okay, 15 past. The thing again doesn't work, but now I'm used to it, right? So nothing new there. I hope that Zoom can hear me over the regular microphone. I can hear myself over the speaker, so I know that you can hear me. And well, I'm all set. I see that almost all of you follow the instructions perfectly, and you sit on the green dot. Those of you who don't, I mean, I'm just not going to look your way, right? And that's, but I have now pointed out that you need to sit on a green dot, not, or very close to it. Good. Lecture 7, EML. Our time together is almost up, right? This is the final lecture that, at least according to the planning, I'm going to give you, at least within EML, right? I mean, perhaps we see each other at some other time. And from next week onwards, Isabel Ferreira will take over. Probably, I mean, I had to chat with her earlier today. That will mean that she will shift to an online-only regime. She has some very good reasons why that is preferable for her. And well, yeah, but if whatever happens, I mean, and I am lecturing again, then I will make a reconsideration accordingly. Good. Yes, one question in the room.
I only want to mention that the slides have to be up.
Yes, exactly. That was one of the things I wanted to mention as well, because I already got a question. I handed in the slides to my team hour and a half before the lecture, and normally they're really quick with uploading things. I've sent now one email and another ping to, like, could you please do this? So I hope this, I expect this to happen very soon. And that I do upload them now, but that's grammatically perhaps not correct, right? But if the effect is that the slides are there, then I think everybody will no, let that one slide. Good. No, but of course they should be online. It makes it easier to take notes and everything. Good. Okay. Well then, let me see. Is there any other service announcements? Not that I can remember. So. Well, I have one warning to issue. I had one of those nights where I think I slept well. My girlfriend told me in the morning that, well, you've been tossing and turning so much, did you sleep at all? Like, yeah, sure. But during the day, I mean, I noticed that I don't know what I did during the night, but I mean, sleep was not one of the things that my brain was doing. So if I get stuck, or if what I says at one moment doesn't make sense, I mean, yeah, it is and remains my fault, but I mean, please be gentle, okay? Good, so to lower the expectations a little bit, such that hopefully I still can fly over them. Regularization. Last week, we finally learned how to assess, or at least estimate, test errors, right? And we could now tell apart, is this a better model than that one? And for example, so near the end of the lecture, we saw that we had a tool by which we can tell, or let's say, these two predictors better than these three predictors. And previously, I mean, well, just by RSS, 3 would almost always be preferred than 2. But by now doing cross-validation, or one of its friends, we'll leave one out, cross-validation, we can now say, okay, well, perhaps sometimes the 2 variable setup is better than the 3. Or similarly, we can now evaluate, is this k nearest neighbor classifier with k set to 10, is this now better than the logistic regression with a polynomial of the 10th degree? Something like this, right? We can now fairly compare things. So that makes us, well, quite well equipped to start applying the methods we've seen. Okay, so wait, in the lecture hall, the volume should be increased. You know, that's what I read on Zoom, but I know that some of you communicate me from the room through Zoom, and some of you communicate me through Zoom from the room. But, volume in the room here, okay? Okay, then it's just a matter that I should stand a little bit closer to the microphone here, and well, then hope that it works out, because the thing is stupid and I can't get it. I mean, it says wird geladen here, and I can press all I want, but it doesn't do anything, so I can't really tell it to use this microphone. And yeah, I'm sorry. Modern times. Good. Now, so that's just as a quick to finish the quick recap. By doing this resampling, we can assess if one model is better than the other. At the same time, each of these models that we're training, well, we can only do this assessment properly after the fact, after we have trained them, right? And that, wouldn't it be nice if we can somehow already nudge in that if we allow, let's say, linear regression to look at 10, 20, 30, or 500 possible predictors, that it's not too greedy. that it does not try to use all of them at the same time, but specifically those that really matter, right? Such that we don't have to do the selection. And you can think of plenty of examples yourself where wouldn't it be nice if these methods can figure out themselves that they should not be too greedy. That is the common topic that we'll be discussing today. That's what regularization is about. Slightly differently put, what we're going to be doing today and the next few weeks, we're going to be expanding on the basic things that, well, we've taught you over the last few weeks. We're going to be expanding the super simple linear model, be it for regression, be it for classification, and we're going to make it a little bit more powerful. And we're going to be doing this in two different ways. We're going to be making it more flexible, because then it can do more cool stuff. And we're going to make it less flexible at the same time. And well, then we're going to combine those two, and then well, magnificent things are awaiting us. So what we're going to be doing next week and afterwards, we're going to be looking into this form, and rather than saying, well, hey, you have to beforehand say that it's just going to be linear basis functions or quadratic or whatever polynomial, right? We already know a little bit how to cheat our way out of the linear system, but going really beyond that. That is more flexible. I'm going to do this later. And well, yeah, we're going to do this with trees and whatnot. I mean, really cool stuff. The less flexible is the topic of today, because that's the idea of regularization, right? I mean, we give the methods the opportunity to touch variables and use data, but it really will need to have a very good reason to do so. We're going to be covering, or recovering, I should say, subset selection, which you've already seen a few weeks ago, right? I mean, how to determine which variables are now important and which ones can we throw out. And you already know forward selection, backward selection, and this mixed type hybrid, right? And that, so I'm going to quickly repeat those just to show, I mean, how we can now make the bridge towards regularization, what we're actually doing under the hood, which you didn't even know yet. And we're going to be looking into what is called shrinkage. And shrinkage, actually the slide I have here already allows me to explain the key idea. So just by looking at the formula here at the top, right? So just in the basic linear model, we have p plus 1 parameters, right? Coefficients. And if we now have many predictors, then we're going to have many of these coefficients. And if we add basis functions, so quadratic, cubic, whatnot, then we have even more of these parameters, right? All of which we need to tune. If we do plain old minimization of the mean squared error, or the RSS, what are we going to be doing? We basically ask the method, try to fit the data as well as possible. And we do not tell it that we would like it to only use the most predictive features. We don't tell it to constrain itself, right? Just squeeze the most out of the data that you can. And as a result, it will, if you can think about it, if you think about it, put these values of beta, not necessarily as high as it can, but it will use each predictor and as much as it possibly can wring out. Put slightly otherwise, those predictors that are really important, for those who want the coefficients to be non-zero, right? Be it negative, be it positive, that we don't really care, right? But for those, we really want linear regression to really use them. And for those predictors that barely have any information towards our target, that basically the method will only use to overfit, right? To basically squeeze out more than it should, to basically go into the irreducible error and the irreducibility that we don't want it to go. Those coefficients should be at 0. We want to shrink them, right? So the general idea of this shrinkage and regularization, how you can think about it, those coefficients that really matter, those values we're fine with, and those coefficients that for those predictors that we don't want it to use, let's shrink them to make them as small as possible. Ideally, 0. 0 means I do not use this predictor, right? That's what we're going to be trying to do. So we're going to take just linear regression and we're going to add some shrinkage on top of it. And then dimensionality reduction, we're going to not discuss it today, but next week onward. So how can we transform our data from something very high dimensional that would have to fit many parameters? How can we now transform the data into something a bit more manageable, over which we would only have to fit few parameters? Black magic, we also call it. It's not entirely black, but okay. We kind of know what is going on there. Good. So let's first go to why do we want simpler models, not just from the intuitive sense, but also from the theoretical, and just answering the question why a bit more properly. As I started in, I think, the first lecture, everything in EML revolves around bias and variance. You have the trade-off in between, right? I mean, if you have a method that is very biased, so it doesn't include the right model in its class, right, for the data that you're looking at, okay, then the variance will be typically quite low because you can trade it off. If we have a method which has very little bias, basically whatever data you throw at it, the correct model is in the class, well, then you need to be very careful that you're not overfitting. Lots of variance is what you're inviting. This you want to balance. What we saw in regression is that under specific assumptions on how the data is generated, Gaussian noise, blah, blah, right? I mean, you've seen this in one of the exercises. The Gauss-Markov theorem then shows us that the unbiased linear model with the smallest variance is just the one where we minimize the RSS, right? That's what you've all by now really should know. The idea is there that essentially we want to, so assuming that the true model is indeed linear, we now want to minimize the variance. That's what it's actually doing under the hood, right? So we know under the Gauss-Markov assumptions that the true model is in our bag of tricks because the true model is linear. So it just comes down to reducing the variance. Now we know how to fit this, but a number of the assumptions that we make and the techniques that we have to use to find this RSS minimizing set of coefficients are a bit prohibitive. So you may remember that it requires this inverse of a matrix and whatnot, right? I mean, which only works under specific setups. Namely, we need to have specifically more data, more rows of data than we have predictors. So the moment that P is larger than N, it doesn't work anymore. We can't do the inverse. That is one of the reasons why we never went there. One of the other reasons is that, and this is basically why does this inverse not exist? That is the true question. There does not exist a unique solution anymore. There exist infinitely many solutions, infinitely many ways of setting the parameters that all will get the minimum error, right? And well, how on earth do you choose out of infinitely many possible parameter settings, right? And that is basically where we said, okay, shrug, we don't know. Now, already thinking back at this previous slide, we don't really want linear regression, Gauss-Markov or not, right, to use all the coefficients at will. We want to use it essentially as few as possible, really the ones that really matter, right? So one of the things that we're now going to be doing is by putting a penalty on overusing, or not necessarily overusing, but using coefficients. All of a sudden, we don't have infinitely many solutions that minimize, but it becomes again unique, right? So just by looking at the fit of the data, infinitely many, but if we introduce a penalty, we can bring it down to just one solution, one other way to look at it. And of course, the moment that we have, through this penalty, I mean, we can identify those predictors are important. This model is better. All of a sudden, we gain interpretability again, because in the infinite possible ways how to set my parameters, and all of them are equally good, there's no way of me telling any of my expert friends which predictors are not truly important, because there's infinitely many ways how I can slice and dice it. Okay, let's go back to subset selection. Blast from the past. Idea, very simple, and hence I'm also going to blast through the slides relatively quickly. We have a number of predictors, and we want to find that set of a certain size, and typically we don't even know the number of predictors we want to choose, right? We want to find that set that is best. We already established there's 2 to the power p of those, right? I mean, exponential, this is too many. We don't want to test all of them. Even if we're going to do cross-validation, I mean, right, it's going to take too much time. We'll also be, it's not covered in the book or in the lecture so much, we'll be reusing the same data too often. So we're testing too many hypotheses on the same data. I mean, I did cover multiple hypothesis testing. So you really don't want to go there. We do know thanks to last week, that if we plug in cross-validation in a smart way, we can tell which size, which number of parameter or predictors to select is now best, right? How to estimate this. There's also other ways on how we can approach this, namely through regularization, by adding a penalty. So we essentially evaluate, we're going to be evaluating the quality of the set, just like we did before, but for larger sets of predictors, we're going to be adding a larger penalty. So basically adding an additional predictor, well, it really needs to bring something extra to the table. Okay, so you know that R squared is a really bad measure, but if you just add more, then it's just going to go haywire. Remember the greedy approach. We start with an empty set of predictors, hence the only thing that we can predict is the average, right? And then we're going to be increasingly adding that predictor that if we add it to the current set, minimizes the error or maximizes some other criterion, right? Depending on which way we swing. So, for example, if we measure it in RSS, then the smallest, largest R squared. This gives us now a sequence of models. We have or basically for each model class, out of the model class of all possible models that include one predictor, we can then identify the best one. Same thing, the best model according to the sequence of 2 predictors, and so on and so forth. And that's what we arrive at step 3. And now, out of these P different possible models, we want to select the best one. Right? That's the greedy approach. Okay, so in one of the next points, I'll also repeat, but let me just do it immediately now here. This is greedily bottom up. We can also do this, starting from the big, from all predictors, and then just cut it down, and we can let it grow and shrink, right? That's, we've seen those variants, right? The core part is not so different. In the second step, we don't really need to go through all the business of assessing the test error, to do cross-validation and whatnot. Right? Because at each step, so if we now, coming from model 1, we found the best single predictor, and now we want to find the best 2 predictors, right? So let's say we found predictor 1 is the best one, what a coincidence. And now we want to see, okay, is 1, 2, is that good? Or is 1, 3 better? And so on and so forth. Now for all those combinations of 2 predictors, we're comparing models of the same complexity, right? Because for each of those, we only have to fit 3 parameters, namely an intercept, beta 1, beta 2, right? So on the penalty on the number of parameters, we really don't have to worry at all. Fair enough, fair enough. So we can just go with training error. For selecting the best model out of M0 all the way up to MP, that doesn't work anymore, because now MP considers all P predictors, and well, hence can simply squeeze out more from the data with P+1 coefficients than model M1, right? Poor model M1 can't do anything, but maybe that is the best one. How to tell? That's where we do need the test error and the equipment that I gave you last week. Okay, so that is basically the story on how we can now do subset selection in a relatively simple way. Suppose that we now want to ideally get away from evaluating the test error explicitly, and we want to incorporate immediately a penalty on the number of coefficients that you add. Makes sense, right? I mean, that's rather than having to do all cross-validation all the time, can we just build this in some kind of penalty? There exist a number of different ways on how to do this. I'm going to discuss 3 with you, of which 2 are essentially equivalent up to some mathematical, well, not even athletics. I mean, it's almost immediately equivalent. And the third one is very similar in spirit to the second one. Let's start with the first one. The CP statistic. Even though it's called statistic, it doesn't really have a sound statistical interpretation. But okay, let's ignore that for a second. Let's look first at the definition. What do we have? And I'm following what the book says. And you'll see in the next few slides that sometimes I take a step to the side to also explain you how you will see it in other literature that is not the book. So what we have here is the RSS, which is normally what we would minimize, plus, hey, look, a penalty, right? A regularizer, as we call it, which is twice the dimensionality of the data. How many predictors do we have? Or how many parameters do we have, depending on how you interpret it? here it's predictors times the variance, or the estimated variance, right? And that thing we do times 1 over n, because in the book they decide they want to have this value per data point. Typically, we don't do this, right? And if we just take CP and we do it times n, right? I mean, that's this definition of CP times n, we have a larger number. Well, who's afraid of larger numbers, right? I mean, not us. And that saves us dividing by n, so that's typically what we go by. It's a monotone operation, so defining by n or not is not going to change the outcome. Still, the best model is still going to have the best score. Okay. What is important to see here, it's trivial, but 2 times the dimensionality of your data times the variance, this is also monotonically increasing if I crank up d, right? The more parameters I include, the higher dimensionality of the data, what you're looking at, the higher this penalty is going to be, right? So in order for a coefficient to now be sort of allowed into the model, right, compared to, let's say, M2 was now the best one, and now we want to add a third coefficient, a third predictor. Of course, the RSS is by expectation going to be go down, right? I mean, we can always overfit a bit, but what is the maximum overfit that we could get? Well, hey, if we go beyond what would be the true set of predictors, we're only going to get the variance data. The variance is the irreducible part, right? Think of Gauss-Markov. So if we now penalize every dimension that we add to our model by the variance, or our estimate of it, right? That's what the sigma hat squared is for. That is the expected amount of information of adding a predictor to your model that actually has nothing to do with what you want to predict, right? That is the idea of the CP statistic. And like I said originally already, if you now really want to sort of go through the theory, intuitively it works, but on paper it starts to break at certain points. But intuitively it's nice, right? So any predictor needs to bring more to the table than just the variance, easy peasy. So by doing so, it accounts for overfitting. If I add useless coefficients, useless predictors that do not bring me more than the variance, well, then that will not be the model that has the lowest CP. And as you will see on the left-hand side, I apologize, Robert. I mean, the next few slides, where are you? I did see Robert. Wait, originally you sat there, you moved. Wait, what? Where? Ah, there. If I say Robert, then you need to raise your hand. I mean, not playing shy anymore. Good. Anyway, yeah. Next few slides. I mean, I still have my pictures on the left-hand side. I try to avoid the flip-flopping, but okay. Good. Yes. Okay. This is not so important right now. This comment. Good. And as you can see, that the CP statistic does go down if we add more and more predictors, but there is now a minimum where this cross is. I mean, the score for 7, it starts to go up. You can barely see it, but we can now uniquely identify 6 is better than 7 in terms of predictors, and 6 is also better than 5 under the CP statistic. From, if you now just cross-think a little bit what I told you last week, from a cross-validation perspective, we had this elbow rule, right? That's one standard deviation from the minimum. You can also apply here. I mean, the book doesn't identify it, but if you just look at it, it makes sense, right? If at, 3 predictors, you're already so close to the minimum that you overall get, maybe those 3 predictors are somehow more important, more informative than the 6 that it identifies as the true minimum, right? This is again where the statistical interpretation becomes a bit icky, but it works in practice, right? So you can also apply the elbow rule here, even though the book doesn't mention it. Yeah, so the last comment, as long as our estimate of the variance in the data is unbiased, so we don't do anything particularly stupid from a statistical perspective, then we can just use the sigma hat rather than the true variance. Makes sense, right? I mean, if our estimate is really off, then of course the penalty will be really off. And yeah, then we're structurally going to choose either a too simple or a too complex model. But if it is an unbiased estimate, which, just to repeat, means that if I give you more and more data, that at some moment you will be able to estimate what is the true variance, right? And that is what unbiased means. Unlike, well, biased, and I give you infinite amounts of data and you still give me the wrong answer, right? And you just didn't pay attention, you could say, but an estimator that didn't pay attention doesn't sound so well in the literature. Good, okay, this is CP, and because of the lack of statistical foundations, statisticians don't really like it. We have others that they do like, even though we can rewrite it almost equivalently to CP. For that, we're going to be taking a very first peek into information theory. Perhaps not even the very first. I mean, perhaps in some other lecture, you already looked into a bit of compression, Huffman codes, decision trees, maybe. I don't know exactly, but depending on who teaches what course, you may have come across those. Ikaika's information criterion is one of the first model selection criterions that was proposed, 1973, at the top of my head. And it is one of those ideas that is now really fundamental, and you see it used everywhere. I mean, even places where you shouldn't be seeing it used. And it's also ridiculously simple. So this is the somewhat rewritten form, where I still use, because this 1 over n and this divided by n, because the book really likes to have this penalty per row in your data, right? Per instance in your data. Now let's do the mental exercise of multiplying the AIC that I have here by n. What do we have? I have a negative log, right, of the likelihood of the data, that is what curly L means, plus k. K is simply the number of parameters in your data, or in your model, sorry. That was the lack of sleep, that's kept in. So how are the number of parameters in your data, just mean as the number, just k, how is this now related to the log likelihood or the negative log likelihood of your model, data on your model? Well, negative log likelihood of your so the data on your model, that corresponds to the number of bits that you would need to transmit under an optimal transmission scheme, right? Has nothing, absolutely nothing to do with just plainly saying, okay, I have k parameters, so I just add k bits. Absolutely nothing. So from an information theoretic perspective, it was more like, okay, this was a first attempt, and like, yeah, okay, now let's wish it away. However, one of the problems of AIC is that it works really well in practice. If you have enough data, it works perfectly fine. You can also see that it's statistically consistent, by the way, just by looking at the definition here. What does that mean? If I give you, again, infinite amounts of data, then the left-hand term, the log L, that will continue to grow, obviously, right? Because the likelihood of your data, every point is again somewhat surprising. And that will completely dwarf the k, or as it is here right now, k over n. Basically, we can completely ignore it. And what we know is that model selection by just log likelihood, and maximizing likelihood, that is sound. If I give you infinite amount of data, you can, by choosing which model makes the data most likely, you will be able to identify the correct model. Right? So AIC is consistent. So hence it's a bit of a monster. I mean, statisticians like it, don't like it. It kind of works in practice, even though it feels a bit icky. Okay, now, without the divided by n, and I put this in the footnote there, this is how you normally come across it in the literature. However, we will be using it right now for the subset selection for linear regression in kind of a special way, right? We make all these Gaussian assumptions. That allows us, for us, to rewrite things as this. This is the transition, Robert, where I apologize for, right? Because we have almost the same content on twice the slides, so, but you know, at least I made one red, right? Red means it is not in the book, right? I mean, that's this is just me telling you this stuff. At least it meant it for this slide. I can rewrite, given the way that we model the data, the negative log likelihood in terms of RSS. That's what I did here. Because now it's just RSS. I mean, now actually we see it in the next slide. I mean, how we can decompose it. But, there is, if we do this rewrite, if we plug in this Gaussian, there is one or two terms that I happily ignore because they are essentially constant over my model class. It doesn't affect the optimization. I will still always identify the best one as the best one, right? So it is not an exact rewrite. It's more like by wishing certain things away. That's what the additive constants, that they don't mind. Now, if I go back one slide, whoops, 2 slides, sorry. You have CP, right? This is the curve that we get. And under this rewrite that I did, with a wishing away some constants, then I arrive at this plot. As you see, it follows exactly the same curve because it's essentially the same thing. I just blurred out the labels of the y-axis because those values are not exactly the same here, but it follows exactly the same curve. It will identify the same minimum for us, right? This doesn't always do this. Now, in our case, this is a happy coincidence. This is good. Okay, so yields the same curve. And of course, especially if you take the way that I wrote it on the previous slide, it's even easier to compute now with all these sigmas and stuff. Where does this now come from? Why can we rewrite it in our case? You're going to be doing linear regression. Linear regression, we're going to be doing least squares. We assume that the world works like this. So it's basically some function over input x with some parameters. And then we have noise, and the noise is Gaussian distributed with some variance and zero-centered, right? This is how we pretend the world works. If we now were to maximize likelihood, trying to find that model that maximizes the likelihood under an AIC, what are we going to want to do? Well, here we look at the probability of y given x and the parameters, right? I mean, that's what we want to maximize. This is going to be distributed in the end, this probability, according to a normal distribution, a Gaussian, where is it centered? It's centered exactly around where our function predicts. That's what it looks like. And then we have sigma squared, the variance around it. It's the error around our prediction. Now, if you already would now sit back and think a little bit, these two things are practically equivalent. Not the value that comes out of it, but the way that we think that the world works. Here we have noise that is zero-centered. And here we have noise. So basically you see the whole probability, but this thing is distributed just where we predict something is going to be. Well, why do we have zero-centered noise here? Because this is an additive term on top of a function that we want to predict. So they're trying to do the same thing, right? And because this noise is now Gaussian distributed, we can rewrite, or basically this is the definition of this, how this now looks like. We have the density function of a Gaussian again. We've seen this number of times, right? So we have square root of 2 pi and so on and so forth, plugging in where normally the mean would go, that we now have here, right? This is essentially what this comes down to. If we take a logarithm of this, then we're going to get this monster over here, these three terms. And what we now see is that here we have n over 2, logarithm of 2 pi. Oh, that doesn't matter to my model, right? I mean, if I look always at the same amount of data, the same number n, that term is going to be constant. I can push it out. Here I have n times the true variance of the data over the entire data. Go away, right? It's going to be constant. And it's not going to affect the choice of a model. Whereas this part over here, well, that part is going to be dependent on my parameters, right? This has f of theta here baked in. And if I now just look at that part, that is going to be proportional to the RSS. Basically captures the same thing, right? You can rewrite these two things into each other, or they are already each other. So in our special case, CP, where we just look at the least squares directly, and AIC, they're equivalent. Okay, good. Well, now let's go to the third, slightly more advanced method. One that means, so where AIC, I kind of love to hate it because it's too simplistic, but it does work reasonably well in practice. BIC, I like, well, actually quite a bit in that. So my professional heart still doesn't fully like it. The third one that I'm not going to be discussing, but in this family, that one I like best. And you may think, okay, AIC, BIC, the third one has to be CIC. No, the third one is MDL, for minimum description length. And perhaps if we meet again in some other advanced lecture, I'll explain you that. But we're not going to be doing this today. What do we have in BIC? In BIC, proposed by Gideon Swartz, 1978. So, well, still before I was born, but not that long ago, right? And on the big scale of things. What he did, and I'm again rewriting things like they do in the book, right? So 1 over n, think this away. We have again a logarithm of L. So L being the log likelihood of this. So this actually then there should be a minus here. Either it's going to be the negative log likelihood and then plus this term, or the other way around. So plus this minus that. I'll fix this in the final slides. What are we doing here? So compared to AIC, we still have the log likelihood of the data. And rather than just adding a penalty or subtracting a penalty k for the number of parameters, we now do k divided by 2. It goes a bit too far wide. I mean, it's basically comes again Gaussians. Actually, Gaussians we can blame in this particular case very well. But what is the magic in BIC? Because just dividing k by 2 is of course not going to give you a very different selection criterion. But we do this now times log of n. And that is a very smart idea. It came from theory, but we can also just get the intuition of this quite easily. If we have, so for AIC, let's actually go 1 slide back, up 2 slides back, 3 slides back. We have here, I can't count today. If we now have a data set of 10 data points, or have a data set of 500 million gazillion data points, the penalty that we now obtain by going from a model from 2 coefficients to 10 coefficients is going to be exactly the same. In the one case, k would be 2, and the other ones would be, well, 10, right? Easy peasy. It feels a bit unfair, right? Because if I have, is it 500 million gazillion data points, I can probably estimate the values for these coefficients really reliably. Whereas if I have 10 data points, well, oh boy, right? I mean, then 10 data points, 10 coefficients, that's going to be a bit tricky, right? I mean, I can uniquely identify my data just by coefficients. That's bad. So AIC makes a boo-boo, so to speak, by not taking into account in its penalty how much data you have. BIC does take this into account by valuing the number of parameters, k, by the amount of data, but not directly, not linearly, but logarithmically. It follows beautifully from theory, although this is one of those classic papers I do not recommend people to read. Many classic papers you should really read. If you ever have the chance or the time or you're bored, whatever, to read Claude Shannon's A Mathematical Theory of Communication, it's a beautiful paper, and it's so nice to read, and it's easy to read too. And you really see like a complete genius at work who's discovering something on the fly, like basically while he's writing, and he's like enthusiastic and amazed himself, but he also completely understands what he's doing. It's beautiful. Schwarz's paper is also brilliant, but it's, let's say, more compact. The brilliance is squished into 1 or 2 pages, and it's one of those papers that you only understand after you understand it, if you know what I mean. Okay, so, but scaling the penalty by the amount of data you have is really smart. Because if I now go from 10 data points to 100 data points, and because we scale logarithmically, right, so the left-hand term, the likelihood, if I now double or let's say tenfold, I go from 10 to 100 data points, you would expect the left-hand term to, well, also grow by a factor of 10, right? If you have the right model, just more data, and then it will just increase linearly, because irreducible error, we can't go beyond that. So the left-hand term will grow linearly. However, the right-hand term, so because of the logarithm, will grow much more slowly. So after a while, it's like, okay, well, now we have enough data. I don't need to penalize so strictly anymore. It's a beautiful idea, and it works really well in practice. The curve is a bit different because of this penalization by data. And as you can see on the left-hand side, it penalizes a bit more strictly. It's more conservative, as we call it. In this particular case, it likes 4 predictors better than 6. What you also see is that it gets, in this example, and this is also generally the case, but not always, right? Your mileage may vary. You get more of a U-shaped, right? There's a slightly bigger dip. There's a more clearly defined minimum. Your mileage may vary, etc. We can, just like with AIC, again, rewrite BIC into terms of RSS. Again, making use of Gaussian, blah, 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 right? I'm not going to go through the steps this time again. You just page back a few, and there you are, right? True, we also have a 4th one. That's the one that I don't like so much, because it's not information theoretic. Yes, question. Wait a second, you have to, I mean, because of the mask, I can't hear you so well. Yeah, so it has to go here. Oh, you can't see that. Here, yeah, so there. Indeed, you're correct. So it's because of the book wanting to have this score per row in your data, they have this 1 over n. Normally not what I do. I will fix this. Yes, okay, that's also let's see, k over 2 to k. Yes, Manuel, that actually is an error. I will also fix this. No, you're absolutely right. I'm not going to tell the people in the room what you wrote, and that's I don't want to identify so many typos. I will fix all the typos very soon. Good. Okay, fourth approach. Personally, I like information theory a lot, so hence I do not like this approach, but people who do not like information theory or are not so acquainted with it, they might also say, well, hey, R squared, that works so well, right? The correlation, right? We could use it in univariate models directly between the input and the output. Multivariate, we can do this between the output and the predicted output, right? I mean, yeah, sure, it has a tendency to overfit, but can't we somehow correct it a little bit, right? Can't we salvage it? Yes, we can. And again, I mean, my information theoretic self says, okay, but why would you want to? Because we can. So how does this now work? You can have an adjusted R squared by, well, 1 minus doesn't really matter. We now have the RSS, and we divide this by the number of data points minus the number of dimensions and minus 1, because you only need 1 to at least have your intercept. And this monster is then normalized by the total sum of squares, where we also have to adapt a little bit, but the total sum of squares is what we can maximally squish out of our data, so we don't bother with the subtracting the dimensionality of your model. As you remember, original R squared will always like more parameters, right? Always like more predictors, so that's kind of useless. But the minus d that we have there, that counteracts this. So maximizing adjusted R squared, the same as minimizing, because this term is essentially constant, right? And that's not going to do anything. So maximizing the entire thing comes down to minimizing this term over here. And how do we minimize that? Well, if we now have a model that is good, and we have the good model plus a bad predictor, right? And a good model may even be the perfect model, but we add a useless parameter, this additional minus d that we have there is going to penalize adding predictors that don't bring anything to the RSS itself, right? Or not sufficient for this adjustment. Now, again, a bit like with CP, the interpretation is icky, but it kind of works. And I think for next year, I mean, perhaps I'm going to deviate from the book a little bit and start with this one, and then CP, AIC, BIC, because yes, it kind of works, but why would you advertise it? I don't understand all the choices of the authors of the book. As you can see here, I mean, we arrive at 7 predictors, so it's even less conservative than CP and AIC, and much less conservative than BIC. Fifth approach, I mean, let's not really call this a fifth approach so much. This is basically just using what we learned last week. Why don't use a validation set? Or why don't just use cross-validation? Yeah, you can do this, but computationally, this is much more hefty. And as you can see, if I now flip between those, in this particular case, they will identify 6 as the right number of variables. So CP, AIC in this particular case did quite well. Adjusted R squared was a bit too eager, BIC perhaps a bit too conservative, which indeed, if you have relatively few samples, it tends to be. Right? So don't use BIC if you have very few samples, unless you kind of want to overfit, right? You want to err on the side of caution, right? You rather want to find those things that are certainly informative rather than going overboard. Good, yeah, and the one standard rule that you've already seen. Actually, it's not so much new on this slide. Let me just skip this, which means that I'm now at this slide, which is exactly where I wanted to be at the break. Let's look at the clock. Well, this clock is 2 minutes behind, as we know from the previous lectures, right? So look, it's 5 o'clock. Let's re-meet here again in 15 minutes. So 15 past on a real clock, so not that one. Okay. So while everybody finds their seat again, and before I start, I have actually a quick question, just out of curiosity, in that because I'm really interested in seeing what is now, let's say, what is the mix that I'm looking at. I already asked in the very first lecture, like who's who, like study subject-wise, right, at which level. But I'm actually interested. How many of you are undergraduates? So how many of you are in your bachelor's currently? Out of, oh wow, okay. It's kind of what I expected, and also, well, if I say hoped, then no, that's actually wrong. I mean, where are the master students, right? Where are my master students at? Okay, but that does confirm that at least my idea of giving this lecture in person. You know, so okay, I will. I don't know what I'm going to do with this, but I'm going to communicate this to my fellow lecturers, at least for EML. And there's a large number of bachelor students. You know, it's disproportionate. Perhaps that means that, especially for bachelor lectures, they should put in the additional effort as well. But, like I said, for Isabel, she has very good reasons. So I'm not sure if she's going to continue lecturing in person, but because I think that. So you're probably, most of you are third semester students, right? I guess. That's okay. Yeah, so I know that Gert Smolka is teaching POC 1 also in person. And I know that a number of the other lectures, so MFE 1, I think went online already, if I'm not mistaken. I don't know exactly, but I mean, there have been lots of discussion, like what is now responsible, what is not, right? There's a lot to say either direction. Good. Okay, now back to what we were discussing. A slightly, well, so no, let me take a different angle. Yes, audio works. Let me take a different angle. What we've just seen are regularization methods. So basically penalization of overly complex models, model selection methods that work in very many general cases. So BIC, AIC, you can use in almost any case. Adjusted R-squared, well, that works better if you have something to measure a correlation over, of course, right? But these are very general model selection techniques that are not specifically tuned or developed for the task of regression, be it linear, be it nonlinear. What I'm going to discuss next with you, ridge regression, is a kind of advanced technique. So hence, I mean, green plus, right? Most of the details you will find in the ESL book. It's relatively modern. It only was developed relatively late in the game. And it essentially takes the idea of, can we now, rather than having a generic penalty that just counts number of parameters, can we now also somehow take into account the values of the parameters? Which, and we develop this now specifically for linear regression. And that, of course, makes a lot of sense, right? If we now take actually a slide back, oops, need to focus here again. A few slides back. Let's go to AIC, where we really just, we have a negative log likelihood term, yeah, and then just K for the number of parameters. We do not look into what does the model actually do with these parameters. Are these now important parameters or not so important, right? That's also one way to look at it from a regression perspective. If we plug in AIC for subset selection, and I only give it predictors 1, 2, and 3, but not 5 up to 500, that essentially means that I'm forcing the coefficients of predictors 4 to 500 to 0, right? I just basically don't give it the chance to even tune those parameters, right? It's one way how to think of it. It's a little bit harsh, right? To really say, okay, no, you're not allowed to touch this at all, but I wanna. Yeah, and then through this backward forward selection, maybe we can find a model that we can just find exactly the right predictors, and then we need to find the right coefficients. It's a bit cumbersome. It's a bit cumbersome, right? Wouldn't it be nice if in one go we can actually give it all 500 predictors, and then depending on how it chooses to use the coefficients, get a very good model? How we can get this done? Yeah, if we have specifically if we have fewer than 500 data points, we can penalize the method. We can shrink, right? We can penalize the method if it puts high coefficients. if it says, okay, this predictor is super important, but actually that predictor doesn't do so much, right? And that's we want to make it pay for really using a predictor for non-zero coefficients. And that is what ridge regression is doing. And in a way, what ridge regression is doing, oh, whoops, where are we? Oh, I should turn off the pen. No, that should off. This is what ridge regression is. What we see here, this is just plain old standard regression, right? As you know it, and just rewritten slightly. This thing here is new, completely new to you. What do? We have here a sum over each of the predictors. And what do we sum? We sum the squared value of the coefficient, right? And we value this sum, or we weigh it by lambda. Some magic value, right? And let's just stare at this for a little bit. If I set lambda to 0, what do I have? I have plain old regression, just as you know it, right? If I set lambda to a very high value, to infinity, right? Infinity is high. Then the left-hand side basically has no influence at all, right? And the only model that we will want is the one that only has a beta 0, because I go here from 1 to p, right? So basically that's going to be the empty model, always. And now depending on how we set lambda, well, the method, the model, will get a little bit more slack of assigning non-zero values to coefficients, which corresponds to using those predictors, right? Lambda is hence very important. How to set it, we'll see a bit later. But if you think about it, 1 or 2 seconds, like, hey, how about cross-validation? Yes, if you never need to set a parameter, cross-validation is your friend. Okay. Like I said, this sum is really from 1 up till p, so the intercept we do not penalize, right? We accept that any model that there will be some average value, right? I mean, this is something that we do not want to meddle with. And this average value, yeah, well, if this average is high or low, is really problem specific, so let's not meddle with it. So we don't penalize this. Now, we can very easily compute already what should be the intercept parameter under ridge regression, under this penalty for a given lambda, if we first center the inputs, which means we compute the average value over a particular column, and we subtract this from each of the individual values, right? Basically means that we force it to take a zero mean distribution, right? That's a centering. What you can also do, we're not going to do this here, but what you can also do is now additionally divide it by variance, which basically means we force it to take a Gaussian shape. This is called standardizing. It's also a very standard technique. And you will see this, for example, in applications of PCA and whatnot, right? So centering, standardization, or Z-scores, also one way how to think about it. They're all within the same family. Now, if you do center, and there's essentially no reason not to center, there are plenty of reasons not to standardize. Centering is not so bad. Then you can directly compute your intercept parameter just straightly like this. From there, how do we compute the coefficients? Well, we want to minimize essentially this thing here, which looks very similar here. This left term is what we've been doing previously, because yeah, nothing changed there. This is just a residual sum of squares, but we have, of course, this penalty all of a sudden, right? So we have beta, the beta factor transposed times beta not transposed, that's basically beta squared, times, of course, then lambda. The bottom right part already discussed. One of the main reasons, and this is completely, well, it is more, let's say, a historical anecdote that I'm going to keep very short. The decomposition of your of the parameter vector over and under ridge regression. So this big R, that's just ridge. It's not to the power R, it's just for ridge, right? Later I'll have a method called lasso or lasso that will have a big L there, right? And that's the only thing. One of the main reasons to introduce this lambda was actually to achieve a non-singular matrix over here. That was what they were originally after, because that has nice properties that are, for us right now, are completely uninteresting, right? So Now I said it, you know it. I'm never going to ask anything about non-singular shapes, right? And that's unless I no, I'm not. No, I'm not. Okay, let's see how ridge regression works for different values of lambda. Just to point out that this is indeed very critical, right? I mean, if I push lambda to a very high value here on the right-hand side, right, that I get a very high value, then the coefficients, they will all go to 0, right? Because in order for a coefficient to be non-zero, well, its squared value times lambda needs to be outweighed by the residual sum of squares, or the gain of it, right? Basically, we push everything to 0. We just go to the mean model. Whereas if we have a very small value of lambda, so here this is basically the value of 1, and then here we penalize heavy, and here we penalize barely. So these lines that you have here, so the red dashed line, the black solid line, and so on and so forth, those are essentially the values of that coefficient that you were to get for that value of lambda, right? If we optimize. It's a bit complicated, but okay. And as you can see, if we have lambda at 0, then the method will happily use all predictors as it can, right? And that's, but if we now increase it, the value, okay, you see some weird bumping here for rating. Here it uses it less, here it uses it more. Why? Well, that's really an idiosyncrasy of the data. But what you do see is that here towards, and once we really start to penalize, so up till here, you would say they're all somewhat comparable, right? All predictors are used roughly the same as even if we penalize less. But this is where the action is, because all of a sudden, income in this model very quickly goes to 0, more quickly than the others. So income is apparently, that coefficient is less important to explain parts of your data than the others are. So that's one nice trick, right? I mean, that sort of ridge shows already that in action, that it's doing something. I'm like I always do. I mean, I always go off script. So let's do this again. I told you that if we push lambda to infinity, the coefficients will go to 0, right? But what happens if we don't go to infinity? So we don't go to infinity and beyond, but we got, well, close to infinity, but not quite, right? It's very bad, let's say, what is it again? Wish version of Toy Story, something like that. That we are in this regime over here, right? High, but what we're going to get is that the coefficients, they're going to be close to 0, but not quite. So if I now would give a model that is not really pushed to infinity to any of you, right? And say, okay, which are now the most important predictors? Then the only answer you're going to give me, like, I don't know. They all look kind of equally important. So what ridge is going to do, it's going to, because of this squared penalization, right? So it wants small values for the coefficients. But squared of small is, well, even smaller, right? So it's completely happy, right? And it has no particular incentive to say, you know what, I'm going to have the most important predictor a little bit higher, and all the others, I'll put them to 0, right? Rather, it will use all of them a tiny little bit, right? Already mean I'm preempting already one of the problems that ridge has. So yeah, perhaps you can think, how could we possibly fix this? Okay. Yeah, the scaling invariance. Suppose that we do normal least squares. So we take a step back from ridge, right? Just also point out one of the other problems that you have with ridge and why we need to solve it. Suppose that I now give you some data and I ask you to do least squares. Right? Okay. Fine, you know how to do it. And I now give you the same or almost the same data, but sneaky as I am, I basically doubled, not the data, but I really just multiplied each of the predictors by 2. It means that x1, right, basically instead of giving you the data over x1, I secretly give you, well, x1 times 2, right? So where every 1 becomes a 2 and so on and so forth, right? Now, what will that mean if we now do least squares for both? You would get essentially the same model with different coefficients, obviously. The difference would be that in the data where I give it multiplied by 2, you're going to get coefficients that are essentially divided by 2, right? And you just need to shrink it back in a way, but shrinking now in a different meaning than we've been talking to before, or about it before. So that is in a way fine. So if we scale the data up, then the coefficients go down, right? It's linear, there's no problem. ridge regression under the same data, right? So the normal data and scale times 2 behaves slightly differently, because in the non-scaled data, we have different coefficients, and the penalization is not linear. It's quadratic to begin with, right? Even if it would be linear, then still it would be more penalized in the one case than in the other. So with normal least squares, you don't have to worry if basically you measured whatever, let's say your gene expressions, right? Learning example so far, whether you had your machine at resolution of 10 or 100 or 1,000, right? Or equivalently, if you just multiply each of the columns by these numbers, doesn't matter, right? You get slightly different coefficients, but effectively the same model with the same accuracy. With ridge, very different game. So what you need to do, you need to standardize. But actually now, we just said that you always need to be careful, but now you need to standardize them. So standardization, let's think about what it does. I mean, we just saw centering, right? Just subtracting the mean. Now we're going to be dividing by the variance. So what we get is a nice unit variance Gaussian. That's basically what our data is going to look like. Which is nice, because now we know, after we have standardized, that for each predictor, it now has the same variance, right? And also so suppose that we measured one thing, let's say, well, height in millimeters, right? And span in meters, something like this, right? And that, so completely off scale. And by the way, I think that all of you know the fun fact that your span is approximately up to a little bit of noise, the same as your height, right? And this is how you measure for old people who can't stand up straight anymore, who have shrunk. They can typically spread their arms and then know how tall they were. Anyway, completely nothing to do with EML. The point was, we have now measured two things in completely different scales, right? Different units. Under least squares, no problemo. Under ridge, well, we would need very different coefficients. You would get different models. After standardization, it basically means that we have transformed it into the same dimensionality, right? To the same dimension, sorry. One tricky thing is, of course, that we are forcing each predictor to be of the same importance. And sometimes certain predictors are not as important as others, right? Certain predictors can just have naturally a higher variance than others. And this is something that ridge is then very sensitive to, right? It will like those that have a smaller spread by naturally more than others. Okay, good. The rest, let's see on the right-hand side. Yeah, so this is the essentially the ratio what you get. Not so important right now. You do know how to compute the coefficients for linear regression. Relatively straightforward by now, right? And let me just repeat, I do hope, even though we didn't require you to do so in the assignments, that if I were to give you a toy example of just a few data points, that you can actually compute this, right? And that, so please do practice. I cannot promise you that it will appear in the exam, but don't be shocked if it does. I'm not going to ask you to compute the coefficients for ridge. That I can guarantee. However, I do want you to understand how it works. Naturally, by including more stuff, it's not going to be easier. At least, then generally, it isn't. Let's see. Yeah, let's actually just start from the right-hand side. I'm just going to do the left-hand side. I might discuss in a bit, but I right now want to discuss the right-hand side. We start with the SVD of X, of our inputs. We already used this a few times, right, to determine what is the best, also for the standard least squares case, right? We already decomposed things. So we have U and V are both orthogonal matrices, and D is the interesting one that gives us our eigenvalues on the diagonal, right? It's interesting. That's useful. The singular values or the eigenvalues, whatever you call them. Now, yeah. So now we're going to jump over here, and then the degrees of freedom, they will appear in a bit. First, for least squares, standard least squares looks like this. We've seen this before. So X times inverse of X transpose X, blah, 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 right? I mean, we've seen this. Hat matrices, right? We remember all this stuff, good stuff. I tried to color code a little bit. in what is going to change if we go from least squares to ridge regression. So this is least squares. And for ridge regression over here, you see that there's plenty of things that are very similar. And here in blue, there we have something new. And whereas previously you could rewrite this as a U transpose times U, here all of a sudden we have something that appears in the middle. Right? Why is this now useful? Well, if we can compute an SVD of X, and we can, right? Plenty of people have implemented this. I mean, we can make use of this. We can now relatively straightforwardly compute in one go the X times the ridge parameters. And we have X, so we have the parameters basically in one go. So the machinery is essentially the same. The only difference is what we have here in the middle. The D matrix, so the middle matrix, diagonal matrix, times then, well, D squared plus the lambda. Why is the D matrix, this diagonal, so basically the eigenvalues, the singular values, why are they so important? And why are they included here? It's relatively straightforward to see, at least intuitively. The eigenvalues, they identify, as we've seen previously, I mean, how important particular predictors are towards the decision, right? That we've seen a few weeks ago. Now, that also means that if I tune those a little bit more, a little bit less, it will have a large effect on my prediction. So if I now take, now I'm going to the left-hand side here. Oops. So what I want to do in ridge regression for a higher value of lambda, I want to reduce the flexibility of the method, right? That's essentially what I'm doing. I'm reducing, you could say, the degrees of freedom. So how much can it move? Now, how can we compute how many degrees of freedom does a model have? We can do this over many different ways, but one way to do it is that for a given value of lambda, we can look at the trace, which is simply summing the values of the diagonal, right, from top left to bottom right. Nothing special there, of the parameter factor we're going to get, which we saw previously, right, and in the bottom right. So this is basically how we compute. This is basically what we'll be computing. The higher these values are, now it's really of the parameter factor, right, in diagonal matrix, yeah, the more I'm going to listen to that particular predictor, right? High values, bad. So the trace of the sum of the coefficients, if that is high, yeah, then obviously, I mean, I have high coefficients. By definition, I need to penalize more. Now, if I set lambda to 0, what do we expect? We expect this trace to sum up to p. Why? We have standardized things. Because of the standardization, we expect it to go to p. If I push lambda to infinity, then I expect the trace to go to 0. Because, well, there is no, I'm penalizing so hard, there's essentially no room for any flexibility anymore. That's what this term here is. Lambda times the identity matrix takes over. Good. Okay, so this is the connection that you have on the one hand with how we can compute how flexible the model is. Essentially comes down intuitively, but just looking at the parameter vector we get, right? And the diagonal, the trace thereof, I mean, the higher the values, the more flexible it is, and so on and so forth. And we know how to compute it. Now, this monster over here, if you do not enjoy matrices so much, you can also rewrite it. I mean, we still need the column vectors of the U matrix, but we can also rewrite it as a relatively simple sum. Try to digest this a little bit. And I know I'm going relatively quickly right now. Try to digest what is ridge trying to do? How is it trying to penalize? Because understanding what the ridge does allows you to also understand when it would fail. And one of the most important things that, well, I haven't like pointed it out explicitly, but I have been trying, as you might have noticed, always to shoot holes. In every method that I've been discussing, I immediately try to shoot holes in it. One of the things I dislike about EML is that I cannot talk about my own research. Not necessarily that I like talking about my own research most, which is actually also kind of true, but mostly because there I know the best what the big holes are. So I'm more confident about talking about them and identifying them, right? The key point of all these basic lectures, also advanced ones, is the moment you understand something, you can tell when would it go haywire? When is it going to go wrong? That's what is important. Just applying something is easy, right? Any bachelor student can do that. At the end of this course, I want you to always be very critical. Like, okay, but wait a second. Should I be applying this? What could possibly go wrong? And trust me, way more than even you can imagine at the end of this course, but be very cautious. Right? Okay. This slide I don't think is that super useful anymore, given that most of the things we already discussed. Why does rich regression now improve? Yeah, well, we penalize, we reduce the degrees of freedom, right? And the more freedom it wants to have, and the higher we put lambda, the higher the penalty is, the less freedom we give it. Fine. We can also again explain it into bias and variance. The higher I put lambda, the bias is. Okay, what is High lambda means high or low bias. I heard mumble. Mumble is not an answer. Robert?
High lambda means high bias.
Exactly, high lambda, high bias. Because you reduce the space of models, admissible models, right? I mean, technically, let's say, yeah, it is possible, but they're going to get such a penalization, right? Very unlikely to be chosen. Very, very unlikely to be chosen, right? So if we go lambda to infinity, well, then we have an extreme bias. Right? Only the average is allowed. Of course, the higher the bias is, so basically the lower, in the rich terms, the higher lambda, the lower we push the parameters, well, the variance will naturally go down, right? We'll make a ridiculous error, but the variance of the error in a way will go down because, well, every parameter can only be set at a very small value, right? So we're not going to make, there's not going to be a huge variance in that sense. The other way around, if we set the lambda all the way to 0, we have within our model class, in this case linear models, we have low bias, and automatically we have a higher variance. Coming back to the whole reason, why do we need the regularization? If I give you fewer data points than predictors, you can't tell out of all the infinitely many models which one is good enough, right? Basically, you have infinite variance. And by adding more and more penalty, then all of a sudden, well, the answer starts to become more obvious. Okay. And yeah, so it is especially effective if the number of predictors is approximately the number of data points in that. Yeah, okay. Well, the bottom thing I now said 3 times. I mean, if you really want me to say it again, then after the lecture. I mean, that's, I want you to think about when things go wrong. I already give you here the answer, so perhaps I should not skip to this slide yet, but hey, I'm a generous, not God, but a generous lecturer today. Rich regression fixes the problem of this uniqueness, right? So if P and N mean they behave in a way, you have fewer data points that you would really want to, Rich does fix that to a certain extent. However, rich regression is typically not your best friend if you want to learn something about your data, if you want to do inference. It will still get you a model that predicts quite well, right? Under the lambda that you've chosen, and well, we use cross-validation to choose it, but it's pretty bad for inference. Why? Answer is kind of on the slide, but I mean, I rather want you to think about it. Why is rich regression pretty bad for inference? Yes, I don't know your name, but you've asked a number of questions now. I want to know your name first. Come again?
Anton.
Anton. Okay, Anton.
Okay, we have a lot of predictors which are often good about bias.
Yes.
So we haven't known which one of them.
Exactly.
Many of them are a little.
Exactly. That is the problem that we're going to get. So just also to repeat for the people on Zoom, rich regression doesn't like high values for coefficients because we're going to square them. So it rather likes small values. And of course, the difference between 0 and 0.0001 or something like this, right, squared, is negligible. And on the penalty side, right, that's negligible. Whereas if I now actually set a coefficient, not to 0, but to something a little bit higher, well, I can still squeeze out a little bit more of my data. And the problem is, if I now have for many predictors, a very low coefficient, but not quite zero, I can still squeeze something out of my data, right? I can still predict something better than just with a flat average. And ridge regression, so even if we were to have a very extreme case, and in practice this will probably work, suppose that we have one predictor for which we would like to have a high coefficient, right? And we now have a high penalty of lambda. We would like this one predictor to have a non-zero coefficient, all the rest zero. Ridge regression is going to smear out this much more over all predictors. Might well be that the one predictor we want gets a relatively high, but not quite as high as we want it to be, coefficient, but many, many others are going to get a non-zero value. Well, how non-zero? That is a good question, because if it's close enough to zero, we can just cut them off, all of them, right? Well, not quite, because in the example I just gave you, there was one predictor which was particularly useful, but suppose that there is like 4 or 5 that are somewhat useful. Well, it's going to drive these coefficients down again, and all the others that are basically modeling only noise, well, they're going to be also, not driven up, but they don't exactly at zero. It'll be very difficult to distinguish the two. So, to rephrase Anton's question once more, what you're going to get with ridge is that essentially every predictor is going to get a non-zero value in the coefficient, right? And hence there is essentially no telling, in extreme cases, absolutely no telling which predictors are useful. You still get a model that predicts quite well, but it's very difficult for inference. You can't really tell. These are really the key points. So we would still have to do a subset selection. Now, the nice thing of ridge regression, this is why it was proposed first, is that it's reasonably easy to compute. Right? We just abuse the SVD once again, right? And we add some things done, right? It's relatively easy. Getting back then to this problem that too many coefficients are non-zero, you could ask the question, well, why don't we come up with a different penalization that really likes zero coefficients? Well, that is the lasso, or the lasso, depending on which side of the pond you're from. Lasso stands for least absolute shrinkage and selection operator. I'm 100% certain that they first had this full name and then the abbreviation, and definitely not the other way around, because that's how it works, of course. And what lasso does is exactly this. So this is ridge. This looks at the L2 norm. What is an L2 norm? L2 norm, we look at the coefficients and we square them. That's the 2, right? What is an LP norm? Well, that is, you take a value and you raise it to the power p, right? You will see this in a number of other courses as well. So ridge does L2. And if we now do L1, so we raise it to the power 1, so we just take the values. So in lasso, what we do, we simply look at the absolute values of our coefficients. Why absolute? Yeah, we don't want, if we have a negative coefficient, to cancel out, a whole stack of positive ones, right? So we sum over all the values here, and all of a sudden, now spreading out a little bit of, let's say, coefficient mass, right, for lack of a better word, so giving all the coefficients a little bit, something close to zero, but not quite, that is actually penalized relatively harshly compared to ridge, where every small value squared becomes even smaller. Right? So lasso, by doing an L1 rather than L2, is more strict on penalizing small coefficients. It will drive it down to zero more aggressively. And as a result, those predictors that actually do have something to say about your data, well, then it's fine. Those will not be driven down as quickly. Lasso will first drive down the useless predictors, and only if we then keep on increasing lambda beyond where we should, then it will also bring down the useful predictors, right, the coefficients thereof. Now, why was lasso proposed after ridge? Because it sounds like such a simple idea where we don't even need to square, right? And it has like a nice name, right, and a good abbreviation. The optimization is much more involved. And whereas for ridge, I could quickly explain it like, look, here's some SVD and whatnot, right? Play with it. For lasso, I'm not even going to attempt. Also partially because the book doesn't attempt, and ESL is also, somewhat sparse on detail, right? That if you really want to know about this, read the original papers about lasso, which are actually quite readable, but it goes far beyond what is necessary to know for EML. That's good. So what we now have So on the one hand, we have ridge regression, which works very well in practice. We're going to see a few examples in a bit. Actually, here you see it already top right. It brings things down, and well, you can for a reasonable value. So it will bring these things down. For lasso, over the same, actually it's the same range of. No, it's not the same range of lambdas. Okay, but well, matched then pretty much. You see, it also drives down income pretty much as ridge does, but ridge then has this weird bump, and it's not quite zero. In lasso, it's bump. Okay, now income is zero. I don't want to use income anymore. And then you see afterwards that studentship and limit are driven to zero, right? So at a higher penalty than at one moment, like, okay, well, they do not give enough information, but it really wants to keep, what is this? The credit rating, which intuitively makes sense, right? If I'm interested in giving somebody a loan or not, then if we're doing our homework well as a bank, then the rating, the credit rating that somebody has is the most informative feature, right? So you can already see that lasso is doing something right. Whereas in ridge, yeah, it mashes everything together because, well, small coefficients are fine, and as long as nothing stands out. Okay, good. We'll see in a bit a few more examples of how this works in practice, and then I'm going to wrap up. Just quickly, how do these things now look? What are we actually doing, right, behind the scenes, or basically in plain value? For ridge, we're minimizing. Hey, look, RSS. But under the constraints that the sum of the non-intercept coefficients has to be below some value S. That's how you can interpret it. If you now rewrite lambda into S, right, there's one way, so you want to keep this minimum. What is lasso? Well, we don't have this squared, but we now just have the sum of absolutes. Has to be smaller or equal. Okay, good. Best subset selection, straightforward as it is, right? I mean, can we also write it? Yeah, of course, we want to have that subset that minimizes the residual sum of squares, and there we have it. But we now want, and this is a bit cumbersomely written, we want to have a set of features of, well, up till, what is it? Up till S, right? So S is now takes a different role than previously, but we allow up till S features. That's what we want to. I is the indicator function that sets, or that basically tells if a coefficient in this particular case is non-zero. And because we now only allow up till S elements, we explicitly force all the others to zero, right? What I already said, I think half an hour ago or so. So these three methods are kind of similar. Subset selection is very harsh. You have to choose, like, I mean, everything is to zero except for the ones that allow it to play with. Lasso, you can see as subset selection that is a little bit less harsh, right? It really prefers coefficients to be zero because then we have the least penalty. But, well, unless they're kind of worth it. And ridge regression is the most permitting, also the most easy to compute, and, well, not, well, uncommonly also one of the best in practice. One of the questions that I've asked in previous EML exams is basically following what we just discussed. Ridge regression, it sucks for inference, right? It just means everything is non-zero, right? I can't tell what is good. Lasso also has some problems. I'm not going to give the entire story in the interest of time, but suppose that I have multiple predictors that are either equally good or almost equally good. Is lasso going to select one, two, or all of them? Well, for prediction, this may not matter so much as long as, well, you get a good prediction. For inference, this definitely does matter, right? If in my data, like, I can determine, let's say, the type of cancer by opening somebody's head, or I can just peer in their eye, right? I mean, if they're equally good, then we might want to know that, hey, they're equally good, right? I mean, that's, and then doctors can choose which is now the best in practice, right? That is not our choice. Lasso may just choose the one or the other. Huh? So that's also not really great in practice because in this example, of course, we do know, but in many cases we don't. What is now the most intrusive variant? Can't we somehow magically combine the powers of both? I leave this question now to you, right? I mean, ponder upon it. The chances of me asking exactly this question in the exam, well, let's put it at non-zero, right? I put some regularizer on it, but I don't know if I drive it to zero or not. But it is a good question. Think about it, right? What are the advantages? What are the disadvantages? How can we do this? How could we possibly achieve this? Let's see. Yeah, not so interesting. I mean, this is basically we already discussed earlier. In Lasso, in this particular example as well. Another interpretation that I stole from the book. Actually, no, and this is also, I mean, this is relatively common knowledge. One other way of thinking about it is geometrically. Suppose that we now have, so under these constraint sets that we have defined here, we can, in parameter space, so this is beta1, this is beta2, suppose that we have only two parameters, right? And we require them, this sum here, to be smaller or equal than S. What does this look like? Well, for Lasso that I have over here, this is the diamond shape. Because if I trade in a certain amount of beta1, then, well, I can get the same amount beta2, right? So hence I get this rotated square. If I look at the ridge penalization, because of the square, this will actually start to look like a circle. Okay, why is this now important? And why does Lasso drive things to zero rather than ridge? Ridge takes anything. If this is now our estimate, right, that we find by minimizing the RSS, then we can look at the contours around it, right? So if I do not allow the parameters that it actually wants, right, because I set it to be, I penalize it through lambda. What you can do, you can draw contours around it. Like, what are then the best models under, I mean, more and more penalization? The moment that one of these contour lines hits anything green, that is the best model. And as you can see in the left-hand side, and this is not really coincidentally, but the chances of hitting one of the corners of this diamond are much higher than hitting something on the side. Whereas on the right-hand side, on the circle, well, the chances of hitting it really on the axis, right? And why is this corner here? This means that beta1 is 0 and beta2 is not. And here this would be beta2 is 0, beta1 is not. Here on the right-hand side, by hitting, the moment I hit the circle, which would be roughly here, neither beta1 nor beta2 would be 0, right? So that's the geometric interpretation. So you have the beta hat, that would be the optimal parameters you really would want to have, right? And you have these contours. The moment that the contour hits what you allow, that's going to be the parameter set that, well, Lasso respectively ridge give you. And Lasso gives you a diamond, and the other one gives you a circle. One way how to think about it. How do they perform in practice? It differs. I can't really tell you Lasso is better than ridge always, or vice versa. This is the stupid thing in machine learning or in data analysis, right? There's always some data where the one is better in practice. Very unfulfilling. As you can see here, the mean squared error, the best mean squared error that we get under the optimal choice for lambda on the ridge. Then we're over here around 30 something. Then Lasso, oh, well, 40 something, right? That is clearly, ridge regression, tiny bit better if we now overlay them. Comes close, but I mean, tiny bit better. If you now want the coefficients to be 0, yeah, then go for Lasso, right? And if you don't really care, then go for ridge. Fine by me. You can also go for a slightly different setup, where there are only 2 inputs that are related to the response and all the rest are nonsense. Well, that sounds like a job for Lasso, because all coefficients, except for those predictors that are useful, should be driven to 0, right? Well, that's exactly what Lasso can do. And ridge, well, given infinite data, it will eventually do it. It will only eventually figure it out. But as you can see, the difference between the solid line, which is Lasso, and the dashed line, which is ridge, and we're interested in the mean squared error overall. This is pretty bad, right? This is quite a gap. It's a gap of 15, or 15 is bad, right? Good. Yeah. This is basically hammering the same point home. Why does this happen? Blah, blah, the left-hand side. I mean, look at it at home, but it's not so important. What you see, if you now look at the estimates of the coefficients under, again, different values of y, so how important is something? The least squares fit is the dashed line. That was the same in both plots. Under ridge regression, you see that, well, we basically the coefficients, depending on how important they are for the predictor or for the target variable, sorry, it swoops just directly by, right? I mean, it's never, so if the variable is not really important for the target, it will drive it rough to, it will be close to zero, but almost never quite, right? Except for really when it's zero. Whereas for lasso, okay, well, the importance decreases. And here we really have an area where it says, okay, no, I don't want to use this, right? I'm happier not using this predictor. In this particular example, you can read two ways. You can read it like, okay, good job, lasso. You did not try to dupe me into thinking this predictor was particularly useful for my target. You can also think it the other way around, like, okay, well, lasso, come on, it is still useful. It's not exactly zero, right? So why didn't you tell me so? Yeah, that really depends on the job that you have at hand. Do you want to make a decision that, okay, this is an important predictor, even though the data doesn't really support it, right? The importance is so weak. Are you willing to take that step or not? That completely depends on the task. If you just want to predict and there's no big impacts on your decisions, fine. Otherwise, yeah. How do we select? Lambda, use cross-validation, easy peasy. Well, that's nothing about it. And you can even, yeah, so this is not so important thing. So you can, you choose some values of lambda that you want to test. You do cross-validation, you find the one that gives you the best value overall. And now if you're interested, right, so this is where you choose lambda. If you're now interested in getting the best possible parameters for that particular lambda, what you may do, statistically it's admissible, to now that you have chosen both your method and degrees of freedom that you give it, lambda, use all of your data to estimate the coefficients again on the ridge. So not just on what you cross-validated, but now over all of the data. That's admissible. What is not admissible is then looking again, as we call it, basically using or over-interpreting any test or training errors that you get, right? Because now you're really double using data, and that's what we did through cross-validation, determine the best lambda. Now we want the best coefficients for that lambda, use all of the data. That you can also interpret again as nested cross-validation, as we discussed last week. Good. Yeah, well, cross-validation, not so important. Tuning parameter, well, it's in certain cases you need a lot. In certain cases you need very little. Use cross-validation. That is my advice also for the rest of the course. Anytime that you need to choose any parameter value, think about how to do cross-validation. And sometimes you can do multiple optimizations, so multiple parameters you can tune in one cross-validation run. Sometimes you shouldn't. Think about the problem that we discussed last week. So think about how to use cross-validation in a smart way, and off you go. Okay, that was it for today. For regularization, was it also for me here? And yeah, well, thank you very much for your attention. And I'm looking forward to seeing you again in person for maybe next course. I don't know. And I mean, if I have to stand in for Isabel anywhere in the next few weeks, then we'll see each other again. Thank you very much. Best of luck with the assignments, exam, and see you. Cheers. Hi.
Why do we even want the parameters to be shrunk down so much?
Because
is it for computation, because you can leave those close to zero out of the picture, or?
So let me also repeat, I don't know how many people are still on Zoom because they can't hear you. Well, there's very few, but still there's more than zero. So why do we want to bring them down? Bias and variance. Okay. Bias and variance, that's what it comes down to. So the more parameters I have to estimate for the same amount of data, well, I automatically increase the variance, right? And that seems a bit meta, call it. alchemistic, right? I mean, hey, we already have this data. Who cares if I now, from the same amount of data, estimate 3 or 4? As long as I estimate the first 3 independently of the fourth, then they're going to be equally good. Yes, but statistically no, because then for each of these estimates, there is some error, some irreducible error, and that kind of stacks up. So hence you want to bring these basically the importance of variables down as much as you can.
Also reduce the error along with it.
Exactly. And similarly, like we saw in the model selection part, like with BIC, AIC, and whatnot, it takes AIC, they really count the number of non-zero parameters. So the moment that you use a parameter, you need to pay something for it, right? So basically all the others are also in a way set to 0 if you wish. Because for few parameters, then I can guesstimate how well I can estimate this from the data. And if I give many, then yeah, well, it all becomes a bit random, right? Is that clear answer to the question? Is that clear enough as an answer? You're welcome. Cheers. Hello.
Yeah, I wanted to ask you a question because I like how you teach.
Yes.
And you make like in the summer semester, you do like for the past years, you've done like another course.
That is true. Yes.
And do you plan to do it like this semester?
This is a very difficult question, whether I'm going to be teaching, well, TADA is the name of the course, Topics in Algorithmic Data Analysis. If I'm going to be teaching this again. So normally the answer is yes. And until earlier today, the answer would have been yes, of course. However, I may need to stand in to teach another course. And hence I cannot give the solid answer just yet.
Yeah, no, sure.
So, exactly. So my intention is indeed to teach that again. And that would be a terrific course to take both after EML or after taking machine learning core lecture.
Yeah.
So because they're jointly, I mean, they're both relatively heavy courses in different ways. So taking them both in the same semester, well, that depends a bit on how engaged you are. But I might have to take over amongst others also machine learning, or it's not also, it's more or. So I will teach a course.
Yeah, okay.
That I can guarantee you. Which course it is, it will be a course on machine learning at large.
Makes sense.
But which one exactly?
Yeah, we'll look forward to it.
Okay, looking forward to seeing you again. So, very good, very good. Okay, doke.
Okay, thank you very much.
You're welcome. Best of luck. Cheers. Gentlemen?
I have 2 questions. First one is about one of the codes, maybe on this slide is okay.
Yeah.
Because one of the legends I believe here the x also. I'm not sure what is meant there.
Basically it's the ratio. So we can just so what is now the double bar 1? You know what this means?
Yeah.
This is the norm, right? I mean that's so what is now the ratio between the norm under Lasso, right, and the normal one, right? So basically, how strongly does it diverge from one another? Is it now going? Are we getting get values that are higher or lower over the entire parameter factor?
Okay.
So that's basically what you see here.
Okay, so especially on the right plot, there are 2 color-coded lines.
Yes.
Is it about the predictor, the different predictors, right?
Yes.
And
yes,
the
exactly.
non-color-coded are
they're basically the ones that are useless, right? So there are the 2 real predictors, right? I mean they're really predictive, and all the rest are nonsense. And as you can see that so depending on how strong you regularize on lambda, because that's basically what this ratio does, right? I mean that's for different values of lambda, they're difficult to interpret. Lambda of 10 or 15, you don't know what this means. So this is how we normalize now from 0 to 1. Lambda is basically behind the scenes. And if I'm now at a ratio of 1 all the way at the right, then I'm at, so a ratio of 1 means that the norm of my Lasso vector, the parameter vector, is the same as the norm of the standard least squares vector, right? Because same value divided by same value is 1. And the other one, right? So if I really drive down my, if I push up lambda, I will go more to the left. Because
to this left.
Yeah, exactly. Exactly. That left. Yeah, not. Exactly. Yeah. So I'm pointing a bit randomly here. So I move more to 0.0, right? Because if I push lambda really to infinity, then naturally the parameter vector for Lasso will also go to 0.
Yeah.
Right. Because Lasso doesn't have the budget, so to speak, to have any non-zero coefficients because
Yeah.
I penalized it so much.
Yeah.
So basically high values of lambda are on the left are at 0.0 or towards 0.0, low values to the right.
Okay.
And now in this plot, what you can see is that at roughly a value of, let's say, 0.1, and this ratio, and you can compute which lambda that is, but it doesn't really matter.
Yeah.
There you do have non-zero values for the indeed the correct predictors, and all the others are driven to zero.
Okay. Okay, so regarding the pink line, I believe it's pink.
Yeah, that's
okay.
yes, that's
So
I think it identifies as pink.
so compared to the green line at 1
Yes.
means the least square and the lasso are about the same, right?
Yes, so exactly. So basically,
Okay.
and what you see is that for least squares, and hence also if we set lambda to 0, right, same thing, then the importance of green is very much underestimated. So it's still in both least squares and lasso, or in pseudo lasso for a low value of lambda, pick up pink. Pink is important, but they don't really see the importance of green as much. There are a few gray lines that are at the right-hand side of the plot are above the green one, even though they're nonsense, right?
Okay.
So basically, what green should be, we should use green to explain the data, but what we're actually doing in this case, we're using all the gray ones.
Okay.
We're using the variance there, the noise, to explain something.
Okay, so what I'm not really understanding is, are normal beta, is the green your predictor in lasso and the normal or the squares, is it the same?
Yeah, so what these are, so each line corresponds to a coefficient for a given predictor.
Okay, so if they are the same, then they are close to 0, right? Like the green line at 1.0.
Wait, okay, let me just re-explain this now from scratch, because now I think that we're starting to talk sideways.
I'm confused, sorry.
Okay, so suppose that you run least squares, right? I mean, that coincides to basically being here. Okay. And the values that we now have, so for each coefficient, for beta 1, 2, 3, I mean, the intercept doesn't matter, right? I mean, that's so the pink one here, let this correspond to beta 1, right? To predictor 1, to x1, right? Okay. I mean, so least square says, oh my God, right? Pink is really important. Okay. Then the next most important one, according to least squares, is this gray one. The gray ones, and then sometime later, and sometimes green, right? Yeah, so if you are now, okay, least squares, I trust Gauss-Markov, these are the most important ones. Okay. No, if you were to do subset selection, you might also be duped. You don't know, right? Okay. Hopefully, if you would now consider the subset pink-green, right? So x1, x2, let's call them that, right? Then hopefully that would give you the best cross-validated, whatever, right? I mean, that's that it should, but who knows, right? I mean, there might be, if you now give instead pink and then, well, these gray ones over here, you might also get a pretty good score, which we don't really want. We want to have a model that includes only those predictors that are true in this particular case, so which are pink and green. Okay. And as you see that now, if we go, instead of doing least squares, right, we're going to do lasso, and I'm going to slowly increase the value of lambda. Oh, yeah, okay, right? That part. That basically means that I move here, right? So 0.6 could correspond, for example, to a lambda of 10. Okay. That means that now for a lambda of 10, if I run lasso, these are the coefficients that I get. Okay, perfect. And now you see that, hey, pink is still the most important. Yeah, okay, I follow. Now it's green, and the rest, they're not quite zero. So lasso still says, yeah, they're quite, maybe your statistical test still says, yeah, this is t-scores, whatnot, right? If we now increase lambda further, this is, let's say, a value of 50, whatever, right? It doesn't matter. Then you see that here, all none, they're really driven to zero. Like they don't add any information. Whereas all of those are really non-trivial. I mean, say significantly above zero. Okay, so the where the line is positioned is not an absolute value, but just how important it is measured or predicted. So the dashed line corresponds. No, not the dashed line. Let's say here the pink line at 1 has the value of 15. Yes. So that is really this just means important and not actually how important. It's, I mean, it is after standardization. This is let's just think about it as the actual value of the coefficient. Okay. So if you just write it out, it would really mean beta 0 plus, well, pink beta times x1
Okay, I
plus
follow so far.
green
Okay,
beta
okay,
plus
yeah, I
x2
believe that
times
I-
x2 and so on and so forth.
Okay, okay, I'm not 100% sure if I am, but so far I believe yes.
Okay, so it's really, so in that sense, the tricky thing is that, so why are we doing linear regression? We're trying to predict a target value. If we truly believe that there's a linear model underlying the data, right, and we have enough data, blah, 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 to estimate, then it would be fair to assume that we find betas that are not just good for predicting, but are actually kind of true. Okay. So that really identify that, well, pink and green are the only predictors that really matter. All the rest are nonsense. And now the left to right, so how much lambda, how much penalty should we add, right? I mean, that's how strict should we be for allowing non-zero parameters? That is now the left to right, well, the ratio.
Okay,
yeah. Good.
Yeah, that's a good that question. I do want to ask.
Let me add one further thing. Let me add one further thing. So, of course, in here we really know that there are two important predictors. All the rest are completely independent.
Yeah, if we don't.
In a real world setting, there's going to be plenty of things that are kind of a little bit important. There's confounded and whatnot, right? So it will almost never look as clear as here.
Yeah.
And suppose that we're now at, suppose that it now looks, even if we drive lambda down, well, not to infinity, but basically here, around here, it still looks like we're over here. So there's still some mess, right? That might lead you to believe that, oh, well, Lasso still likes it, right? I mean, those predictors are also important. And how important? Well, they are, well, one or two important, right? I mean, that's if you just look at the y-axis.
Yeah.
Basically, what you always need to keep in mind is that if you're doing linear regression, unless you really pray to the right gods of data science, you cannot interpret the coefficients directly as having any relationship to the true data generating causal model.
Yeah,
they are just coefficients that you now found to retroactively explain your data, and depending on the penalty you get this or you get that. And if you in linear regression you don't do this, but in plenty of methods you have some randomized, so we looked at the likelihood maximization, and then things become randomized, and so it can give you some insight in which predictors are important. Look, but are they now 5 respectively 10 important? No.
Yeah,
no. But
yeah, because I believe that was making the conclusion.
Yes, exactly.
Because you said it's the ratio between them, and I will compare the absolute value on them. Okay.
Yes, it's the ratio between the. Yeah.
Question solved so far.
Good. Okay.
Yeah. Sometimes it's really nice being a fly on the wall and listening to other people's work. I actually, one of my questions was just like really stupidly, because I was confused regarding the direction which lambda would scale.
Yeah.
I was like, why is lambda going up? Because like in my mind, it's always to the right, it goes up.
Yes. Yeah. For me as well. I personally, I hate these normalized plots. Yeah. Same thing with the k nearest neighbor. And you might have noticed that every time when there's such a plot, I also need to like, yeah, I don't need to do the mental arithmetic. That the book loves them. And it's one of those things that, yeah, once you see it, then it's obvious, right? Then it's helpful, but yeah, I would also flip it the other way around.
Is the bend something characteristic about the Lasso in general, or is it just the data set that they're like above the green and the pink line, close to the dashed line, have a bend that goes like quite steep down?
That is reasonably standard. It's reasonably standard. And so you can probably think of, I mean, if you do the legwork, so you see that green is brought down to 0 before pink, right? So basically what Lasso will do, I mean, think of the diamond shape, right? I mean, that's the more we penalize it, basically the more we shrink thing, right? The more easy it is to hit one of those corners. That is essentially what is happening here. So we are hitting at one moment, so that we shrink this diamond so much that it's very difficult to not hit, let's say, a green corner, because it's like a multi-dimension. It's not in 2D, right? When you have then many high dimensions, difficult to imagine. But hitting one of those corners is super easy. That is the moment where we hit the green corner. So green is now regularized out. And there's still, well, we still allow them for pink, right? The high dimensional diamond is not shrunk well enough such that we also hit 0 for pink, right? And that is why we get a non-zero value. So what you're going to get if you now start with a very low value of lambda, right? All the way on the right-hand side of the plot. So that basically means we have a giant high-dimensional diamond. And now we do this expansion, right? And the chance that this blob around the parameters that least squares would really want, that it hits our big diamond, that it hits it on a corner, that not so high, right? The more we shrink this diamond, the more likely is actually that we don't hit it on one of the faces, but we hit it on one of the corners. That is the moment that something is brought down. And we can already see that in this plot, what is the moment where the diamond is being brought down to a small enough size for this to happen? This is exactly at the dashed line. Before that, you see that all the other points, they're still, all the other lines, I have to say, they're not at 0 yet. Some of them may be, right? But the majority is not. So that basically means we still have a high-dimensional diamond that allows the contours around the RSS contours to still hit on one of the faces rather than on the corner. And until that moment, lasso doesn't really do its job. And at dashed, and then it really starts to do its job. So what you will see if there's multiple important predictors, more than 2, what you typically see is that they're going to be brought down one by one, right? Just like you see here, green, less important than pink, right? I mean, that's so bring down green first, and then we bring down pink. And suppose that blue is more important than pink even, right? That one will be brought down later. And the tricky thing is that they're going to be brought down one by one, and it might be that green and pink together are in a way more useful than blue, even though blue we need a high coefficient for it. So you should not interpret it that green is less important than pink, than blue, than whatever, right? So the order in which they're brought down, you need to again be very careful. The only thing you can see here that, okay, all the gray ones, they're brought down significantly earlier than pink and green.
This is just because of the negative shows that we have like some that is 2 and 2 that are distinctly useful.
In this particular case, yes, in this particular case. So you can also see that if you now were to have a number of other predictors that are kind of useful, they will probably be brought down to 0 a bit earlier. But then it would be very difficult for us to determine, is it now, suppose that this is purple, right? We also have purple brought down a bit earlier, right? I mean, okay, do we now have 3 important variables? Or is it now actually green and pink and purple is just, well,
so
free riding?
We can't be sure about the significance of the respective variables, but can we also can't use the ordering as useful information because of synergy effects, right?
Exactly. Well, we need to be very careful with this. So confounding.
I mean, the more you look at it, the less useful it gets. Because like it's good, but this.
Yes. You always need to be really careful. And basically all the problems that you currently see, and we'll see also in the future, in that of applications of machine learning and its friends in the wild, they all come down to, well, people making assumptions that do not hold in practice. And one of which, namely confounding, that is the one that everybody's like, yeah, it's not going to be that bad. It is. It's really bad. Yeah. And people think it's not so bad because we as humans, the way that I see it, we have sort of a causal engine in our head, and we can kind of see if 2 things are now related or not, right? I mean, that's if let's say the light would slightly dim for a second, right? I mean, at that moment, like 500 million gazillion things happen at the same instant across the world. Was this now caused by a butterfly flapping its wings somewhere in Tibet? Or is it more likely that the operator who was actually doing the electricity plant here in Saarbrücken sneezed and actually, accidentally pressed the button and quick? Well, we would jump to something closer by being more likely, but technically we don't know. We just apply our understanding of how the world works to this, right? And hence, for us, it's not easy. We're also pretty bad at it, but at the same time, exceptionally good, of telling what could now be possibly confounding effects. If I give you a set of possibly confounding effects under your understanding how the world works, you can strike through quite a few, like, okay, this doesn't matter, that doesn't matter. These definitely do. The problem is that the computer only sees data and doesn't have a world model. And it can't sort out like, well, yeah, if I now have a column with butterflies flapping their wings, relevant. It can help me to predict, right? So that's one of the difficulties, I mean, to sort out what is now confounding, what is not.
Slightly related to that, it's also one of the bigger things I noticed, like more on the topic. Because when you're like naively looking at some people talking about like this is our great machine learning system and it does so good at object recognition.
Yeah.
This is like 90% sure it's something.
Yes.
That doesn't mean actually anything about probabilities. It's just like how the activation function is spiking out.
Yes. Yes. Exactly. Exactly.
The more you know, the less trusted are you.
Absolutely. Absolutely. And it's.
This is in the wild. Yeah,
and it's really been it's bewildering on how brittle these systems are, and at the same time, I'm also often very much amazed by what is possible, until I scratch my head. Okay, what are they actually doing? Right. So GPT-3, I don't know if you've played with it or saw it in action. Right. This is a big language model. It's really it's amazing on what it can do, and how it can complete sentences and can assess how close are words and whatnot. Sometimes it almost feels human, and then it does things like, okay, what on earth? And so you are very easily trapped into attributing, say, a higher intelligence value, right, for lack of a better term, to such a system that does something that you think, oh, this is, for a human, this is pretty high level. But, and for me, the big eye opener that I had in years and years ago, I was still a student, master student at the time. And together with two friends of mine, we were in charge of the robotics laboratory back in Utrecht, in the Netherlands. And one of the things that we did alongside with that, we were tasked with organizing I think it was a monthly, let's say, a get-together of all faculty, where there were some drinks and some snacks, right? A bit like at the kickoff, right? I mean, that's outside, right? And that was also organized from Fachschaft, basically.
Yeah.
But then specifically for the professors, and that was very nice, a sort of a mingling there. And we had in our robotics lab a number of robots, and one of them, actually many of them, but the one that we built for this, was wheeled, it could steer, it could roam around, right? And that, and we made we stacked something onto it, and there was like a platter, which there were drinks and some snacks, right? And it would then roam around the audience, right? I mean, that's and I overheard multiple times when it roamed around and it sort of drove, right? I mean, that's and just people say like, oh wait, yeah, it's recognizing the color of your shoes. See, it's going because you have brown shoes. You have white shoes actually, but okay, white shoes. It loves white shoes, and you see it doesn't like black shoes, right? I mean, that's no. I mean, I programmed the thing myself, and it was if you see something close to your right-hand side, turn left. If you see something left, turn right, and otherwise move. And perhaps there was a bit of randomness, something like this, right? Yeah. But it was just been a Breitenberg vehicle. And not also a beautiful book to read. The book called Vehicles by Valentino Breitenberg. It's classic. Very simple control structures that give rise to relatively complex behavior. But then you have highly educated, highly qualified people, right? I mean, that taught me about AI. They're like, oh, it's doing this. Like, no, it's just doing something stupid, right? So it's very easy to attribute things to. We need to be very careful there. But and sometimes it's also the other way around. Sometimes getting something simple to work requires a lot of brain power. But what is now simple and what is hard, we are very bad at guesstimating that.
Oh yeah.
Okay, so I actually have another question.
Yes.
Can you go back to the slide where you said here, minimize the RSS subject to, I don't know. Yeah, exactly this one. Okay, so here in ridge regression, we have L2 norm and a lasso L1 norm. That's fine. Okay. When I saw the slide, I was wondering if we can, with subset selection, also formulate as a problem which involves a norm or so. Well, and I immediately, I firstly thought it's L infinity norm.
So what is it?
Infinity norm. But when I thought about it, I'm not sure about that. And when I thought even more, I thought, okay, L infinity norm doesn't seem good, but the
It gets in a
possibility
direction,
is
but
L0 norm, but that's not as well as it would be normal.
exactly. Yeah.
Okay,
So that's basically what you get. It's essentially it's an L0, but I mean, it's really in this particular case for subset, it's really you would not do a smaller or equals, it would always been equals, right? In subset selection. I mean, that's essentially it's just by definition a combinatorial optimization problem. I mean, find me those S, K, or these two out of the space of all possible, and how we now implement it typically is in this greedy fashion, which may dupe you into thinking it's optimization problem that is sort of continuous-ish. But it's not, because normally you would really want to explore the space of 2 to the power p possible subsets.
Yeah, exactly. Well, the thing is why I thought about this. I believe it's in the slide after that where we have the 2D plots of the norms, like where the
yes. So how people
L1 norm is the diamond and the L2 norm is the circle.
Yeah.
And the L norm would then be a square, right? I believe I have seen a diagram regarding that.
Could be, yes.
I believe it was in the machine learning collector slides. I'm not 100% sure.
Yeah, that could be. I'm not sure if there's another L0 or if that is the L infinity.
I believe it was the L infinity norm.
I'm just going to go along. Yes.
Yeah, because that was the moment where I thought about, okay, this doesn't make sense anymore.
No.
So we just cannot write that in terms of a normal. So.
Not really. It's also like it's a very different optimization problem by definition. What people do with these types of combinatorial problems, subset selection is one of them, right? And that in the end, it's just combinatorial optimization. People do try to relax it to having a continuous optimization problem.
Yeah, I know.
And for example, for making the IOP or something like this, right? And that's and then in the end, I mean, rounding things or doing something horrible to it, that does often give quite reasonable results in practice.
Yeah.
But whether this is allowed in theory, right? And that's by the theory police. That depends a bit on the problem.
Okay.
So
yeah, that basically already was the question, because if we write it like this, I think the question can occur naturally, because the norm. Yeah. Okay. Also, not also norm.
No, but not really. Right? It is a norm. So in the end, I mean, it is for the best subset selection. It's also the L0 norm would then be S, right? That's how you can read it.
Yeah. Because
that's the only coefficient that we strictly allow, right? I mean, so you can read it as an L0, but yeah, for the optimization, it doesn't help you.
It doesn't work.
No.
Yeah.
So,
okay.
No. So this is more like a bit of a stretch that, look, you can see it as constrained search.
Yeah. Okay.
So, and just helps for a bit of insight. It doesn't make things easier. Which way, I'm afraid. Okay. Good.
Yeah, your topic of convex optimization, which is already starting there, is complicated.
Yes.
I'm not proficient in that, unfortunately.
No.
Okay.
Good. Yeah. Okay, gentlemen.
Thank you.
Unless there's further questions, I'm going to slowly but surely round up.
Oh, I believe Zoom. I hope Zoom didn't have any questions.
No. So that means I have the chat open here, but there were no questions. But otherwise, I would have stopped you.
Yeah,
I'm not a monster.
Yeah, it was now. We talked about half an hour or so. Yeah.
Yes.
Okay. Yeah. Thank you a lot, actually.
Thank you very much. Thank you for your attention.
Yeah.
So